Hello, everyone. Welcome to our second session in this October RoboLaunch series. Today, it's my pleasure to introduce Luli. Luli is a research scientist at the Biorobotics Lab at Carnegie Mellon University. His research focuses on cross-disciplinary robotic system science and engineering, including the study of novel mechanisms, electronics, algorithms, and system architectures for real-world challenges. He has been leading research projects involving biologically inspired mechatronics, such as biomimetic tactile and visual sensors for non-destructive inspection, capable annual-shaped robots for disasters such as search and rescue missions, and neuroprosthesis, restoring muscle functions for wounded veterans. He had also mentored more than 100 students at CMU, from undergraduates and international visiting scholars to master's and PhD students, some of whom are the rising stars in academia, industry, and new technology business startups. Today, he will present part of the work he has been doing in the Biorobotics Lab at CMU with Professor Howie Choset. So, without further ado, Lou, please, the floor is yours.
Thanks for introduction. Hi everyone, it's an honor to meet you guys online. And today I'm going to introduce our Biorobotics Lab to you. Since our co-director, Professor Howie Choset, is traveling today, so I'm going to stay here long and show you a wonderful story and what's the cool research we've been doing at the CMU Biorobotics. So quick introduction for myself and also our lab. My name is Lu Li, and I'm a project scientist working at the Biorobotics Lab. We're one of the biggest lab in the Robotics Institute at Carnegie Mellon University. So our lab covers different research disciplinary, but our niche is confined space. So we build robot, like for example, small snake robot can go into human body and also disaster site to save life, and also to help industry and the society to improve our life and to save life. And additionally, we also work with key aerospace manufacturing companies to build the next generation robot to go into, for example, airplanes, also critical infrastructure to repair them. And lastly, we also carry out several fundamental research, including modular system, manufacturing on space and also on Earth, and last but not least, medical robotics. So quickly show you one of the cool robot we built several years ago. So this mostly Professor Howie Choset and his students' work is the modular locomoting robot. As you can see, the two robots is dancing on the floor. There consists of 16 identical modules. So that's another term we also like to call it modular snake robot, because each of the joint is pretty much the same. So we can modularly connect them together to form a snake-like structure. So in this case, it's a snake, which can crawl, can dance, can move around. You may want to ask us, how this robot can help society? Well, one case is we've been able to deploy our snake robot into a decommissioned nuclear reactor. So typical use case for snake robot is it can crawl into small spaces. Like for example, here's a video of the snake robot crawling inside a steam pipe inside this dysfunctional nuclear site. And we're able to go in there, reconstruct a 3D map, and also identify potential defect. And that information can be sent to a base station outside the pipe to infer where's the location that we need to take care of. And as you can see right now, we have a student and staff putting the snake into this super tiny pipes, and the snake's able to send the information live back to the command station. Additionally, our robot have also been deployed at certain disasters. For example, this is one case we sent our snake robot to the Mexico City earthquake around 2017. So we're a couple days late, but we're also able to work with the first responder on site to send our robot into the collapsed building and try to locate survivors. So this is one of the use case of our snake robot. Additionally, we also, during the COVID, also built another snake robot which can swim under the ocean, under the sea, to be able to provide situation awareness underwater. And as you can see, this robot is also like a snake-shaped robot. But the cool part is using the modularity, we are able to quickly design two types of new modules, which is a lateral propeller and also axial propeller, to quickly change our snake into a fully submersible underwater capable system. As you can see in the video, the snake is able to traverse through complex pipelines under ocean. And we also, just a couple months ago, sent our robot under a naval ship to inspect the rudder and propellers. And this robot is equipped with both an onboard camera to provide visual inspection capability, and also we have a payload module potentially can add a new sensor in there to provide better see-through and maybe sonar inspection capability. And this robot is quite maneuverable, also nimble. As you can see, it can swim through a 6-inch pipe under the ocean. And also, more importantly, this system can fully operate it in total dark environment because we have a onboard illumination and also control software to be able to provide a long-term surveillance, long-term inspection without human intervention. But currently, this robot is still kind of teleoperated or semi-autonomous control because in our research portfolio, autonomy is one of the key components we like to add on to our snake robot. And this is one of the students swimming next to our snake robot to showcase that our robot is not only capable, but also pretty safe to operate with human around it. So I think early on, I mentioned one key term, modularity. So that's going to be one of the focus in later talk. I'm going to show you how modularity can enable different type of robot species to solve real-world problems. For example, here's the one use cases of modularity in action. And this robot we call Eigenbot because it's kind of both an inside joke or something. We try to find what is eigenvalue for robotics or what is a minimal functional module that you can use to build a robot. So in this 2-minute video, you're going to see our unpublished next generation system in action. So currently you can see this robot is a nice looking, cool hexbot. But conventionally, if you want to change the shape or the function of robot, you need to hire a bunch of grad students to reprogram them. But in this video, you're going to see we are using just our hand to disconnect the leg of the hexbot and then introduce 2 new functions. In this case, it's 2 rotating wheels at the back of the robot. Without any programming, our robot is able to figure out what is my new body type, what is my new configuration, what is the new wheel introduced to my locomotion control strategy, and how I can compensate. So the secret sauce for this is modularity, because it's not only a mechanical modular system that you can toollessly reconnect, but also this is a distributed intelligence platform, which means each of the joint actually have a tiny, tiny computer in there, try to calculate what my locomotion behavior should look like. If there's a new wheel or this new function, how I can use my newly introduced function and computing power to solve the locomotion problem. So within this quickly demonstration 2-minute video, you can see we turn a hexbot shaped robot into a 4x4 wheel vehicle without any without any reprogramming. The only human intervention is go in there, unplug the leg, and put a new function module in there. So the motivation for creating such system is during our real deployment at the search rescue site, we realized conventionally you need to put a full function robot into a backpack and carry them far away to a disaster site. But occasionally you also want to change the form of the function robot. So this is extremely hard using current technology. So we'd like to propose this new modular philosophy that enable first responders to quickly build robots as if you're putting Lego together. So pretty much they can build a robot to fit the disaster scenario and use them to deploy in the wild. And we also build a super, super cool robot. It's a sister robot of this Eigenbot. It's a human-sized hexbot. So we're reusing the modularity. In this case, each of the red joint is an integrated actuator with both integrated sensing, control, and power. So this robot are also able to quickly assemble together using a minimal amount of time and resources because the control philosophy is also extendable to robot as small and large. And so you may want to ask, hey, how can we extend this smaller robot control into this bigger robot control? The key point is modular intelligence. So in our lab, we also have a team of students looking to potentially like reinforced learning based and deep learning based method to teach the robot how to learn based on my new shape and allow them to tackle different type of terrain problem using this newly introduced wheel geometry. So If you like to work on such type of problem, also let us know. We can connect you with the right team within our group. During all this cool work in search and rescue, we also realized one of the key challenge in current robotics is confined space. So confined space normally are defined as a space that's enclosed, also pretty tight for human or even current generation robot access. As you can see in this three picture, confined space in industry, military, aerospace are quite challenging. So sometimes you have to send a human to crawl into the small spaces, which is normally toxic, dangerous, it's not ideal for robot to work, but we still have to perform certain type of missions, for example, inspection. And in certain cases, as shown on the right picture, people need to do welding in such tight space. So how can we replace human with a robot? Because in this case, we're not replacing the workforce, we're putting people away from a dangerous site. So one of the robots we built maybe 10 years ago, this is actually my first project when I started working at CMU. It's a small transformer crawler robot, can go into an airplane confined space to perform switching, fastening, and also inspection tasks. So in this case, we're using computer vision to understand the location of the robot in this super tight wing box. Fun fact, the airplane wing is actually also the fuel tank of the airplane. So it's super, super toxic because the aerospace fuel. But currently we still have to send human worker into this tiny tight space and to perform microscopic surgery in the airplane. But as you can see over here, this robot can, using this integrated 5-degree freedom robot arm in the front, to be able to change the configuration orientation in these small spaces and deploy a end effector tool and also 3D sensors to capture the 3D scenario, also place a fastener onto a certain location. This robot, alongside with the other one we call telescoping arm, which is also another redundant arm, which can stick into small spaces, but with pretty articulated motion are able to, in this case, draw an airplane inside the airplane. So we can also make this video as a joke. But the cool research behind this is how to control a highly redundant robot arm in a small spaces to plan its motion for certain target tasks. But during this several projects, we realized another bottleneck in confined space robotic is, although we can build a super capable robot can perform all this type of cool tasks, we couldn't find a sensor that's small enough to fit into these tight spaces, also are able to see an object really close, because conventional 3D sensors are normally designed for example, autonomous driving or other application doesn't have this sensing distance constraint. So to answer this problem, we actually create our own sensor. So this is a sensor we call Blazer. It's pretty much the world's smallest 3D sensor that you can attach to the end of the robot arm to use the 3D scan information to guide the robot arm where to move and how to move. So as shown in this video, sorry, we have to blur the robot out because it's one of the robots being used for real aerospace industry. And our sensor is able to recreate this high density point cloud, which is a collection of 3D points to define a shape of a geometry. So we're able to use this sensor to guide the robot arm across a sealant structure to apply sealant in the airplane. And maybe after, right before COVID, a 12-hour genius student also come up another idea of how to use this sensor. So as shown in this video, they're able to combine our sensor hardware with a software toolchain called SLAM. And in robotics, we call SLAM simultaneously localization and mapping. So we're able to combine our confined space sensor and the SLAM technology to give a result like this. You're able to handhold our sensor, just wave it around toward the object, and we're able to recreate this colored 3D reconstruction of the environment. And because it's a project during COVID, of course, we have to put a face mask into the environment. This is pretty cool, but you may ask, how can we use this sensor? So right after we finish this project, the US Department of Energy reached out to us because they're having a big problem need to be solved. So as you probably know, or probably don't know, we have a lot of pipeline underneath us. They are the key backbone to supply material, fuel, and in certain cases, also electricity and water around our city to support our life. But most of the pipeline are built almost 100 years ago, they are still falling, they are starting to falling apart. And there's extremely costly to repair them. Like, for example, based on the Department of Energy, it's costing about 5 to 10 million per mile to repair a natural gas pipeline. So how about we combine what you see earlier, modular robotics and confined space robotic to solve this urgent real-world problem? We actually send our robot into one of the real pipelines. So this is one of the video we're able to collect inside the pipe. As you can see, the pipe actually pretty dirty and also with a complex geometry. In this case, it poses a real-world challenge that how can we localize our robot once we send robot into this super long corridor of pipe, everything looks the same. The answer is SLAM. So we actually built our robot with this custom design sensors, which are able to project a laser ring onto the surface geometry. Our SLAM algorithm is able to recreate the 3D reconstruction map and also the accurate location within the pipe. So in this video, we're able to pretty much capture the data and then recreate a fly-through effect so that you can manually, artificially fly through the pipe and able to inspect the surface condition of the pipeline. And so here's step one. After we're able to collect the information of the pipe, we're also able to send the point cloud into an artificial intelligence enabled defect detection framework to pick up the defect. And then we are also building a second robot following this inspection robot to be able to repair the pipe if we detect, for example, a crack, a leak, or a damage. So in this project, we're working with the University of Illinois. They have made this wonderful material, which is 3D printable and is normally shaped, it's a gel-like, but if you introduce a thermal trigger, this material can quickly harden and turn into a hard plastic, which is sometimes even stronger than metal, but also as flexible as a plastic. So we're able to build a robot to carry this material and also extrude them inside the damaged pipe. So in our future vision, this will be the way we can reduce the cost of pipe repair by changing the philosophy from open up the road, putting a new pipe down there to a in situ or minimum invasive robotic repair philosophy, which we can send robot into pipeline, repair them without digging all the road up. So this project is supported by the Advanced Project Research Agency within the Department of Energy. And so I think I just mentioned, can we use this type of robotic technology to repair the critical infrastructure? In parallel, we're also thinking about maybe we can apply the similar sensory control and also repair strategy into manufacturing, because we probably heard about the term 3D printing, or more professional way that people like to call them additive manufacturing. If you already have a 3D printer, like I have one behind me, they have a lot of problems. If you actually print something, you'll realize any 3D printer, they are follow an open loop process, which means you load a print file and the machine will just execute without understand what's been really laid out in the real world. And that is highly likely to result a print failure in a lot of cases. And most of the commercial 3D printer also doesn't have a way to inspect the printing result. So to solve this problem, we propose a new method, kind of a new philosophy for 3D printing, is what if we can add a modular sensor onto your system as a modular add-on and start taking information as if we're building like a robot clocksmith are able to inspect what the defect we generate by our manufacturing process and potentially able to repair them on the fly. So there's one project recently we've been working on is how about we add this new closed loop philosophy, which introduce an inspection element and also introduce a repair element onto a conventional manufacturing system so that we're able to collect information both from the reference geometry, also actual geometry, and compare them using artificial intelligence to pick up defect. And then we're also able to replan a manufacturing trajectory, or in this case, it's a 3D printing path to avoid obstacle or to refill a negative defect. In some cases, for example, there's a void in your part. And we're able to create a system like this. If you have obstacle in your 3D printers, our printer is able to use this tiny eye to understand the defect and then actively replan to avoid obstacle. In this case, the orange part representing a constant defect, and we're able to quickly reduce this geometry tolerance to the actual perfect part geometry. And later on, we also demonstrated if you have a negative defect, for example, here's a void in the part, we're also able to, using robot, to automatically to fill up or to patch this void to repair the part as if you're having a perfect geometry. And recently, we also got a Best Paper Award for the IEEE IROS conference. The paper title is Toward Closed-Loop Additive Manufacturing, Paradigm Shift in Fabrication, Inspection, and Repair. And more detail, you can refer to this paper. And if you want to join our team, let us know. And for potentially next summer, if you're going to join our lab, one of the projects I'm going to work on is apply this additive repair onto a real-world system that can print metal. So in this case, we're actually putting a metal welder system onto a big robot arm. So hopefully next summer, you're going to see our robot start printing metal that can be as big as maybe a car. And additionally, we also start thinking about, hey, once we have this automatic robotic repair system, can we build a 3D conformal circuit that we can attach or directly print onto our future robot, so the robot maybe can have some force sensing and computing capability right onto the robot skin. So lots of exciting project. One of the motivation why we want to print such type of electronic onto our robot is we want to keep reduce the size of our robot we design. And because eventually, in dear of our heart, we really, really wish we can use our robot to save life. So medical robotics, that will be another big topic heavily emphasized in our group. And maybe 10 years ago, Professor Howie Choset and his students started this company to make the super, super small medical snake that can go into human body. And in this case, you're watching a live CT image of the snake robot swimming next to a human heart perform surgery. In our field, we call this minimal invasive surgery because compared to conventional open surgery, now you can just have a tiny access port to send your robot in. And a lot of time, patient can leave the hospital with a single day because you don't have a major opening and people actually doesn't suffer as much compared to conventional surgery. We also recently started looking at, can we apply the sensory-based control and also the snake robot design philosophy into a bigger type of system? In this case, as you can see over here, we're putting our sensor and also end effector onto a bigger robot arm to form automatically needle insertion. Because in critical care, sometimes before you're actually able to treat a patient, you have to insert a catheter or biosensor inside our femoral artery. So in this case, we're using robot to insert the catheter. So maybe in the future, if there's a mass casualty event, the first responder will be a robot. And last but not least, we're also thinking, can we apply what we learned before? Not only apply robot system into industry application, can we also collect all the data from the future generation medical device and collect them together to build the next generation telehealth platform? So this project is a project we started over the COVID, which we team up with a researcher group from University of Pittsburgh to create a robotic ventilator, which in this case, we're adding all this sensor actuators technology from what we learned in robotic into medical field. So we really wish we can reduce the cost of medical device and also increase the intelligence of next generation medical system. With this in mind, the RoboVan is also another cool project. If you're going to join us next summer, you can be part of. And lastly, maybe let me introduce you to another project which we haven't released to the outside yet. It's the artificial lung project. Conventionally, you probably saw the previous slide. If you're really sick, you can put people onto a ventilator. But what if your total lung function is failed? What we can do is putting the people connected to an artificial lung device, which in this case actually not that difficult. Is artificial lung composed of two devices. One is a pump to circulate your blood, And the second major device is oxygenator. So pretty much you're adding oxygen back to the bloodstream. So these two devices sound simple, but actually it's not. In the real world, this artificial lung is a gigantic contraption, which normally you have to put them all the subcomponents into a big car. And there's thousands of people actually living on this machine every day in the ICU. So in our vision, what if we can shrink all the device into a small backpack so people can actually live on this device, go into daily life without worry about dragging this big car neck to you. So the challenge for this project is actually twofold. One fold is, can we apply what we learn in robotics and to help medical device people to redesign the next version of smart medical device? The second is, there's a trade-off once we shrink everything small, because in engineering, we have this term called safety factor. So the medical devices are big because they're designed to be bomb-proof, so never fail. But once we shrink everything to this minimal size, there's always a chance one part, like for example, the wall thickness will be slightly skinnier compared to this ICU grade device. So they're more likely to fail. But what if we combine the technology from machine learning and artificial intelligence that we can collect or harvest all this machine performance data and predict when the device can fail, and then trigger alarm way before the device actually can fail to send the patient back to hospital to replace the potentially faulty part. So there's both the advanced medical device component, also the machine learning component, which are looking for talent students to join us. So that's all cool, exciting thing about everything happening on Earth. But let me take a quick pause and show you the other exciting things going on at Biorobotics, which is space robotics. Because everything I just showed you can also happen on Earth, but the same principle can also apply to space problem. And in this project, we're actually also looking for students to join us next summer. This project is called Space University Research Initiative. So we're joining forces with several universities and also research lab across the United States, try to actually build the next generation space robot that can repair and service future satellites. So there's three major components in this project. First is inspection. So what if you have a satellite or maybe the International Space Station have a big leak? How can we solve the problem? So conventionally, you need to send a human astronaut on, go outside the spacecraft and put a patch or replace a circuit board. But in the future, we're going to send a mission vehicle to orbit really far from Earth and even to the moon and Mars. And in those missions, we're not allowed to quickly send astronaut go into the problematic satellite. Maybe the solution is, let's also send the robot over there. Or maybe the robot already stationed next to the orbit that can fly to your faulty satellite and repair them. So that leads to the second big research focus is maintain. How can we maintain a defunction or decommissioned satellite? So a lot of cases, because space actually a pretty clean environment, the old satellite, they're just running out of fuel. If we can fly over and refuel the satellite, we can quickly save a lot of money and also extend the life of the old, for example, telecommunication satellite. Lastly, think about long term. You also saw what the slide I showed earlier. We can use 3D printing system to repair, to build a structure that you've never seen before. We can also do space 3D printing. So how about we combine everything that I showed earlier? Let's build a spider robot. Let's carry a 3D printing manufacturer with a bunch of sensors that can build space structure on orbit. So in that case, we only need to send raw material and our giant spider robot into space. And then this robot can just build a big satellite and potentially a energy generation solar panel array on our orbit, and that can refuel our next generation vehicle that go to Mars and space. So if you want to join us, there's contact information. You can reach out to Jordan, which is our rockstar postdoc leading the team. All right, so that's a quick introduction for most of the interesting project happening at Carnegie Mellon University Biorobotics Lab. So let me now change the gear and show you what's our expectation for new student. So our team is quite big. So normally we kind of like to mention there's three requirements we like to see from our next generation researchers. So first and foremost, research capability. So we like to work with students with this strong curiosity about everything. You want to learn, you want to join us, and also you want to be self-motivated because as you can see, we work on a lot of problems. So sometimes we're mostly self-organized, or in certain cases, we like to hear what you want to work on, what you like to help. So that will be the first thing we like to mention to our newcomers. Second, we need person that is hardworking, also a team player, because you're not going to work alone. We're going to help you, and also you're going to work in a team setting. And then there's two contradictory recommendation I like to give people is first, be a generalist, because if you want to work on robotic problem, you have to know everything, because robotic means you are a mechanical person, you're an electrical engineer, you're a software programmer, sometimes you're also a biologist, and a lot of time you said earlier, you also need to know a little bit of biomedical. So be a generalist, learn everything. But you also want to be an expert in small aspect that you can truly contribute to your research team. So use myself as example. I'm a mechanical engineer by training, so I'm pretty good at mechanical engineering. But during my years at CMU, I also taught myself to be an expert in embedded systems. So I can design circuit board and functional system really small that you can put into a robot. So that's my expertise. Second is communication. Because working the world-best research lab, one of the key components is you need to be able to communicate your research with the outside world, with your peers. So you need to be able to present your work clearly and professionally in both academic setting, also to speak up to general public. And additionally, we also like to write papers. We want to collect our thought, also documented what we learn, and also present it into a written fashion. So you also need to be a good writers. And lastly, since we also have tons of students in our group, the best way to communicate between our student and our professors is go through what we call weekly report process. So we have a pretty cool website. Once you join us, you'll know that. Go to this website and lay down what you've been working on this week, what your plan for next week. It's a self-motivated, self-organized group, but we also like to start documenting everything you've been working on. So that can be a written documentation that future student can join the lab and quickly pick up your work and continue your research. Lastly, service. Let's help each other. I always like to mention this to the new student come to our lab. We're not the lab that we're going to force you to work on something. We're the team that we provide a platform to enable you, enable the community. So let's all work together. Let's build a robotic community. Let's use robotic to solve real world problems. And lastly, let me close up with this cool picture I think I found online when people starting to form the team, go to Antarctica for the first expedition, they put this advertisement on newspaper. So building robot, solving robotic problem is not easy. We're truly looking for brave people to join us. It's not going to be an easy task, easy path, but I'm going to promise you it's going to be a lot of fun. You're going to love it. With that, let's conclude my talk. I guess I'll open up for questions.
Well, thank you very much for this, Lou. It was really awesome. Yeah, thank you for taking the time for sharing the lab's work, and of course for sharing opportunities to these students. I'm sure they will benefit a lot from that. And yeah, we're starting taking questions now. So the first question we have is, thanks for speaking with us. I am a biology and mechanical engineering double major, and I would love the opportunity to meet with you in the future. Um, um, would you be willing to have a short one-on-one conversation with me in the future? He's interested in biorobotics, surgical robotics, and biomedical engineering. So I can connect you to him if you're interested.
That'll be great.
Um, so next question is actually from me. Uh, I was wondering when you were talking about the surgical robot. What are the challenges of decreasing the scale so much? Because when you're trying to I suppose that when you try to assemble those modules, you end up with some slacks, all these things. So do you need to come up with a different design maybe, or are you able to use the same principles?
Yeah, that's a great question. Actually, that's a question keep me awake every day. Is how we can shrink a robot into smaller size. So actually, there's a three problem. Once if you try to shrink your robot small in that size, one is mechanical, like you mentioned. In our case, the surgical robot actually is totally different in the locomoting snake. So in the locomoting snake, all the motors inside each of the joint. But in the surgical snake scenario, you couldn't find a robot that's both small and powerful enough to fit into each of the segment. So in the surgical case, we have to put the motor outside the snake and then using tendon to drive the snake. So that's also one of our secret sauce I can only show you once you join our lab. So that's a problem one. Number two is sensing. So yeah, we can build a snake, cool mechanical structure, but the robot couldn't understand what's inside your body. That can really cause a harm if you use that system to do surgery. So adding the proper sensing and also consider what type of sensing modality is needed and also crucial for medical surgery, and also able to find the sensor or even design your sensor that can just fit into the tiny space we have. That's a critical part. And last but not least is a term we call state estimation in robotics. Using the sensor, can we understand what is the position of your snake robot tip and what is the condition that your snake experiences inside the human body? So understand that. That's a key research also currently going on in the lab.
Oh, okay. That sounds very exciting.
Great question.
Um, oh, thanks. So next question now. Thank you for the inspiring presentation. This work is amazing. So uh, this the two questions in one. And the first, for undergraduate students that are interested in learning more about the lab, how can I explore some of the most recent projects? And two, how can the best fit for my interests and skills?
That's also a great question. I think there's twofold. To understand the latest work from our group, we have a website, but to be honest, our website is 4 years behind our actual work. Maybe the best way is talk to us. So I think I put our email onto the screen. It's called biorobotic@andrew.cm.edu. So our team really like to chat with you to understand what's your background, what is your interest, and then pair you up with an actual project. So that's, I guess, also kind of semi-answer the second question. Since our group is quite big, I think only showcase maybe the 30% of what we are working on. So I'm pretty sure we can definitely find a group match for you to line up with your interest and background.
Well, I thought the scope was very broad, but it's if it's 30%, that's even more impressive.
Maybe I
So
got a number wrong.
sorry.
Maybe I got a number wrong. Just kidding.
Next question. What has been the hardest thing of taking robots into surgery, and how do you think it's the best way to work alongside healthcare staff to make it more and more common?
That's a good question. I need to think about that. That's a really great question. So for that, I think from what we learn, at least based on my limited experience, observing the actual experiment happening when deploying the robot onto either an animal or a human, that's for conventional technology, we still require the human to tightly operate the robot. And that's going to be a fact and also going to be a requirement for a foreseeable future. We need to build a path that allow the future regulation agency to understand there's maybe the intrinsic safety going on in our software. And also from our responsibility, we also need to make sure how we can build a stack of AI system that can guarantee the safety when operating surgical robot onto a human, because that's a life-critical event, life-critical system. Currently, I think toward this goal, I don't have a clear answer. That's also something maybe we should work together. But safety is definitely the highest priority for surgical robotics.
Okay. Oh, great. Yeah. Um, Um, one more question. Um, why modularity is so important within robotics, and what directions are you most excited about in robotics?
Can you repeat the second question? I got
Oh,
the
the
first.
second is, what directions are you most excited about in robotics?
Got it, got it. Yeah, I can answer that question. So the first is in terms of modularity, actually, we have a three direction going on in the lab. First is modular hardware. Can we create a modular robotic Lego that can plug together and form a new function? And the second is, what is the critical software that can behind this modular connection? Like, for example, the video you saw earlier, within 2 minutes, you can change the shape of robot, but there's a lot of secret magic software hidden behind it. So in terms of, like, for example, modular communication, and also secondly, how to share the computing among each distributed computing unit. So that's the software research. And third, and actually that's also something I'm super interested in, is can we create a software tool that can generate a build plan for future modular robot? So that's also kind of answered your other question, what's the need of modular system? Because like I mentioned before, conventional robot are fixed function, fixed structure system. But based on needs, sometimes we want to reconfigure our robot configuration or arrangement to form a new form of robot. Can we automate this process? Like maybe in the future, you can tell the AI system, can I have a robot that can go into an earthquake disaster site and to find survivors and deliver drug? And then this AI system will tell you a build plan. For example, you need to use module A, B, C, connect them to A fashion, and then here's a software suite you also need to preload onto your system. So this will enable the next generation first rebounder robot to become not a robot, but a bag of modules, bag of functional modules that you can quickly reassemble or even service and repair in the field if one module fail, because apparently robot can be damaged in the real world.
Yeah, um, definitely. So another question that also touches on this modularity aspect is, um, the fact that we don't need to reprogram the robot makes it much easier to work with. So, what are the potential impacts you see on this being used in education to, for example, um, get children excited on robotics and these
Yes.
things?
Yeah, that's definitely one goal in our mind is what if we can reduce the entry barrier for robotic? Because currently, to be honest, you need to take a lot of courses in computer science, in engineering to be able to master the art of robotic programming. Maybe in the future, we can have more natural language as input to program robot, or even maybe the robot can be self-assembled, self-organized into a functional subsystem without human intervention. In near term, yes, this is definitely a great tool that we both want to extend this robot you showed earlier as a general educational platform. And more importantly, we also like to turn the robot into a generic testing platform so that you can uh, upload new control software, you can upload new neural network-based algorithm onto our platform to test robot in the physical environment. Because if you work on any modern machine learning problem, you also heard about the term people call sim to real. Like everything learned from simulation is really hard to apply to realistic scenario. So in our philosophy, what if you build a modular system, you can quickly stress test, prototype your robot algorithm in the real world. In that case, you can bypass simulation because you're doing everything in the real. So you don't have the sim to real problem. So that's our hope. Turn this into a generic educational and development platform to enable the entire robotic community.
Oh, I'm excited to see this in the real world. Yeah. Um. So, next question: what are the best personal projects to work on to build an impressive portfolio before applying to jobs and or graduate programs for surgical robotics and medical device design?
Let me see. For that, normally our recommendation is when you apply for grad school, you want to show the breadth and depth of your research. Breadth means you need to cover at least maybe two different disciplinaries so that to showcase you have a broader understanding of the entire field. And the depth means you also need to focus on one deep theory or deep engineering problem to showcase that you have the capability to solve graduate level problem. So in robotic and medical device project, I think the couple one I showed you earlier, one is the automatic needle insertion. That one can show you or teach you the fundamental of robot kinematics, control, and also potentially computer vision and machine learning. So that will be a really highlight project I'd like to have new student working on. And the second is the artificial lung project, because that project is really try to push the state of art of modern medical device. So there's a lot of problem, like even me, I don't know the answer. So that's going to be more research type of question. We need to really work as a team to combine both people from engineering department, robotic department, biomedical, computational biology, all together to solve this common problem, which the entire community don't have a solution yet. So I think these two projects I'll recommend to start with. But all the other projects, once you reach out to us, we can also show you everything in details, and maybe you can come back to us to say which one interests you most, which one you think will be the first project you want to work on.
Cool. That's awesome. Um, One more question. Um, if I am interested in using my skills to make an impact, how can I communicate this in my statement of purpose? I think everyone talks about impacts, but this is really what drives me. What would you
Sorry,
advise
could you
in?
repeat the keyword you mentioned?
Oh, I'll start again. If I am interested in using my skills to make an impact, how
Impact.
can I? Yes, yes. How can I communicate this in my statement of purpose? I think everyone talks about impact, but this is really what drives me. What would you advise in communicating my interests and how I hope to contribute? Being part of a team and working hard together is really important. It seems like the team is doing amazing work to help people.
Yeah, that's an excellent question. So maybe we need to ask ourselves how to define impact. In my opinion, a impact project, impact research is a project like no one being able to solve. It's a challenging, tedious problem our entire field is either struggling at or people try to avoid. Like for example, in the infrastructure repair problem I just showed you, that's a problem still being solved by human. They put a lot of manual labor, hardworking people to just crawl into the pipe to do the service and repair. That's the problem. That's a typical problem in automation and robotic community. Sometimes we try to avoid. We like to say that's a too hard problem. That's maybe for the future robot. I feel like that's the project actually have the highest impact, because if you can solve a problem like no one else can solve, a urgent problem that can really change people's life, that's a highly impact problem we need to work on. So go out there, explore, work on the hard problem, work on the problem no one can solve, no one want to touch, or you're the only capable people want to try to solve, or maybe build the pathway toward the next solution.
Yeah, work on the hard problems. I think is one of the best advice you can give to students.
Yeah.
Um, and so we have another a question from Joshua, who is a student at Howard University in Washington. He's asking if these opportunities are also available to students outside CMU.
Yeah, I think yes. We have this wonderful program called RISS, Robotic Institute Summer Scholar Program, which you can Google that online, and that's our pilot program. That's our best starter program. That's enable student outside CMU to join us during the summer to become a official CMU RI researcher and join our project team.
Yeah, and I can speak for myself here. I'm from Brazil. I was at CMU this last summer as part of the Robotics Institute Summer Scholars Program, and yeah, I highly advise everyone here and applying to. It's an amazing opportunity. You meet a lot of very cool people. We work on amazing stuff. You see a lot going on. There's always a lot going on in the RI. So yeah, it's awesome for and the applications are due January. So it's good time to for you to start thinking about statements, maybe your statement of purpose projects, and This week and the following week we'll have a couple more talks, so you can um, like have an idea of the research going on and what opportunities you'll have to work on. For you specifically, Joshua, you seem to be interested in healthcare. And on Thursday, we'll have Zachary Erickson, who works in caregiving robotics, giving a talk for us in RoboLaunch. So you're very welcome to join. I hope this helps. This answers the question. And these were all the questions for now. Do you have any final comments?
I think that's a thank for giving me opportunity to showcase the research being carried out at Biorobotics Lab. If you're interested, feel free to reach out to us, reach out to RoboLaunch event, and also most importantly, if you want to join us, apply for the RACE program for next summer.
Perfect. Yeah, thank you very much for this, Lou. This was awesome. Yeah, I love that. I love to see the lab's work. It's really awesome. The impact to have. It's yeah, we're very grateful for the work you do. And well, thank you everyone that attended this. I hope this was inspiring and helpful for you as it was for me. And well, bye. Take care. Thank you very much.